7.8 Inverse trigonometric functions. What's the difference between a reciprocal function and an inverse function? Make sure you can answer this question correctly before going any farther. And you should Google, you should do whatever you need to do to go back and find a good answer for yourself. In trigonometry, as in algebra, inverse functions are extremely useful. However, trigonometric functions present a persistent challenge with regard to inverses. They, all of them, lack a critical property required for a function to be invertible. What is it? Again, search for this, go back and take a look at your old resources. We last discussed invertible functions in chapter 2, but if you simply run a Google search for invertible functions, you'll probably get the requisite information. In case chapter 2 is a bit dusty, let's think about the problem a different way. We know that the cosine of pi over 4 equals the root 2 over 2. What other angles have the same value of cosine? Well, if you know your unit circle well, you would say, well, I know that the cosine of 7 pi over 4 is equal to root 2 over 2. I know that the cosine of negative pi over 4 is equal to root 2 over 2. And there's a lot more. We could draw this out on the unit circle. It's all those angles that have the same coterminal side. So, right, negative pi over 4, 7 pi over 4, etc. Now, let's move on. Let's keep this an idea in mind. Number 2, the cosine of theta is equal to root 3 over 2. What is theta? What is theta? Well, I look at the cosine of theta equals to root 3 over 2, and I say, I think that theta is pi over 6. But my friend says, no, that's not theta. I think that theta is 11 pi over 6. And then our other friend says, no, you're not right either. Theta is actually equal to negative pi over 6. And now we have quite a to-do. So which of us is right? We've got 3 potential answers. They all satisfy the cosine of theta being equal to root 3 over 2. Let's try that again. The cosine of theta equals root 3 over 2 with 0 less than or equal to theta less than or equal to pi. What is theta? Well, cleverly, what this idea of theta being greater than or equal to 0 but less than or equal to pi does is it restricts us to quadrants 1 and quadrant 2, which means that only in one quadrant is the cosine positive. So we only have one option. This means that theta must be equal to pi over 6 for that restriction of the domain. And this leads us to the idea of the inverse cosine function. The inverse cosine function is defined as theta, so it produces angle values, equal to arc cosine or inverse cosine of y, where y has to be between negative 1 and 1, and we will output angle values of theta from 0 to pi. Now let's do a quick check for understanding. I want you to evaluate the following functions, and you should try doing these yourself to see if you can work through it. I'll come behind you. Inverse cosine of 0. This is asking us what angle theta has cos theta equal to 0. And the answer, inside of theta being greater than or equal to 0 and less than or equal to pi, The answer here would be pi over 2. Now, the next one, it looks pretty similar. The cosine of 0 to the negative 1 equals, and we might be tempted to say that this is pi over 2. After all, cosine to negative 1. But no, don't do that. No, 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 no. When you put the negative 1 on the outside, it means reciprocal. It means 1 over the cosine of 0. And the cosine of 0 is just 1. So that's our final answer to part B. Now, last one, cosine inverse of negative 1. Well, this is again asking for an angle value. It is in fact an inverse function. And we need to just ask ourselves where in the arc of 0 up to pi does cosine take on the value negative 1? And it happens at pi. Similar, what do you think the value of the inverse sine of negative root 2 over 2 should be? Okay. Well, if I think about this on a unit circle, negative root 2 over 2, the sign being negative root 2 over 2, happens in two places. I could have 5 pi over 4, or I could have 7 pi over 4. Both of these will have negative root 2 over 2 as their sign value. Actually, there's another option. It could be negative pi over 4. And in fact, negative pi over 4 is the one that we go with. The reason we choose negative pi over 4 is that because we would like our inverse sine function to operate on two connected quadrants of the unit circle. So we would like it to be able to trace a continuous sweep through two quadrants. It doesn't work to say start in the first quadrant and then work your way all the way around to the third, because we would have to pass through that quadrant, and we don't want that quadrant. Similarly, we can't use 7 pi over 4 on because we would have to get there, and we don't want to pass through both of these two. That's not good. So what we say is start at negative pi over 2, work your way up to 0, and then keep on going to positive pi over 2. Might feel a little weird, but I promise you, it works the best of all the options. So here's how we define inverse sine. The inverse sine function is defined as theta equals inverse sine of y, where negative 1 is less than or equal to y is less than or equal to 1, predictably. And let's fill in those blanks. Theta is going to be between negative pi over 2 and pi over 2. Okay. Now, consider theta equal to the inverse sine of 0.8. In what quadrant does theta lie? Well, any positive argument and that's the argument, corresponds to an angle in quadrant 1. Because we're only working, the only quadrant where we had positive sign values, remember, is right here. Okay. Now use a calculator to determine the value of theta in radians to 4 decimal places. So your calculator has a button that is inverse sine, sine to the -1. And what you would do is select inverse sine and then simply plug in 0.8. If you do that, you should find that you get 0.9273. And remember, that is radians. Now, we're going to step out of unit circle world to think about the xy graph of tangent before we move into talking about its inverse. And here's the reason why. The tangent function was peculiar, we should say, because it had asymptotes. If I was going in my negative direction, I would have that. So you remember how we wanted to keep these inverse functions operating in contiguous blocks as much as we could. So when we think about the graph of tangent, we have all these different swoopy bits. If we're going to consider the inverse of tangent, we should take one. We should just keep one of these. We should just, because the truth is we've just covered all of the possible values of tangent with that one sweep. So it's sufficient to have that particular chunk as the one we use for the inverse. Let's continue to tidy. So the idea there is that just like sine, when we think about the inverse tangent function, it runs from -π/2 out to π/2 in terms of the angles. Oh, oof, my. Wrong. It runs from -π/2 to π/2 in terms of the angles that it outputs. But there's an additional piece here. Look at our function right here. What are the original y values in tangent? Are they limited? Remember, for sine and cosine, we were always restricted to be between -1 and 1. For tangent, we're not. See if you can fill these in. What is the actual spread here for y? Well, if you said from -∞ to infinity, you're correct. You're thinking about it the right way. Now, note well, you will also see inverse sine referred to as arc sine, inverse cosine referred to as arc cosine, etc. And you should be aware of this dual notation. I think I even used it accidentally earlier. It's very common. So let's just do some practice. Try running through these and look for me to fill them in. I'll add some color commentary as we go. Okay, the first problem, the inverse sine of √3. So the question says, what angle has the sine value of √3? And remember that that angle would have had to be between -π/2 and π/2. But wait, we actually have a problem. √3 is bigger than 1. Sine never reaches any value bigger than 1. So because this thing is bigger than 1, the inverse sine isn't defined. This does not exist. Important to keep that in mind. Okay, let's move on to part B. The arcsine of -1. So remember, arcsine just means inverse sine, and we're asking what angle measure within our restricted domain has, or within our restricted output rather, has the sine value of -1. And that would be -pi/2. I'm going to keep moving through these. The inverse tangent of √3, well, that's going to be first quadrant. So that would be pi/3. Inverse sine of 1, that's pi/2. Inverse tangent of 0, asking again what angle corresponds to tangent being 0. Well, that's when sine would be 0, because remember that tangent equals sine over cosine, so that happens at 0. And inverse tangent of 1. Inverse tangent of 1, arctangent of 1, that would be pi/4. Tangent of pi/4 is 1. So the arctan of 1 is pi/4. I want to draw your attention back to C before we close. We started out by saying we couldn't evaluate the inverse sine of √3 because √3 was bigger than 1. However, the inverse tangent of √3 corresponds to pi/3. There's no problem there. Remember, the inverse tangent can be evaluated for any argument. It's defined from -infinity to +infinity, and that's because of the nature of the graph of the original function, of the tangent function. So be careful with inverse sine, inverse cosine. You can be a little more free with inverse tangent. Remember that for all of them, you have to work inside of the output restrictions.